Thank you very much. Sorry. Thank you very much. I want to start by thanking the SEA for awarding me this prize and for giving me the opportunity to speak here at this conference. I did my thesis under the supervision of Carlos Barceló, Raúl Carballo Rubio, and Luis Garay at the Institute of Astrophysics of Andalucía. And in this talk, I want to explain shortly the main idea or the main discovery behind this PhD thesis. And for this, I want to start by explaining why I chose this picture for the background. This is a work of art by Anish Kapoor. An important part of his work consists on painting things with black, in particular using a kind of black paint which is called Panta Black, which absorbs nearly 100% of the incident light. In this particular installation, which is called Descent to Limbo, he creates the optical illusion by using this black paint that we cannot distinguish whether he has painted a circle on the ground or he has actually dug a hole and painted the walls of the hole with black. Curiosity killed the cat. In this case, it was an Italian tourist who fell inside the installation, which actually turned out to be a 2 meters deep hole, so he broke several ribs and ended up in the hospital. Perhaps they should have put some warning signs or a fence, but this would have killed the dramatic effect of the installation, right? This is another picture which explains what I was just saying. By looking up front to this work, by using this perfect black paint, we lose any perception of depth. We lose all that information. If we were able to cut transversally, we would see that this is really a hole. And why am I explaining this work of art here? Is because now we have this picture, this image. I think it needs no introduction. Is the image of the central supermassive black hole of M87, photographed by the EHT collaboration. And I could argue that we are facing a similar situation here. Surrounded by the light of this accretion disk, we have a dark blob that in principle hosts a supermassive black hole. But this object is so dark that we lose any information about its structure, and we cannot distinguish whether there's really an event horizon there or there's a different kind of object lurking at the center of M87. In my thesis, we start from this idea, and we try to postulate alternatives to the well-known astrophysical black holes, and we try to question whether they could be different objects. But it's not a coincidence that black holes are nowadays the most well-accepted candidates for these dark and compact objects that we observe. There is a combination of theoretical and observational reasons behind it that I will explain in this talk. But first, a little bit of story. In 1916, Schwarzschild derived the first vacuum solution within the theory of general relativity, which was shown to the community a year before. And the theory of general relativity tells us, in essence, that gravity is curvature, that space-time curvature tells matter how to move, and matter tells space-time how to curve. The Einstein equations are the cornerstone element of this theory. On the left-hand side, we have the Einstein tensor, which encodes this geometry of space-time. On the right-hand side, we have the stress-energy tensor, which describes the matter content of the space-time. By a vacuum solution, we understand a solution to these equations where the stress-energy tensor is zero. There is no matter involved. And the Schwarzschild spacetime is just the most idealized model that we have of a black hole. It's spherically symmetric, is eternal, and has no inflow of matter whatsoever. It's just an approximation. At first, this solution was not clearly understood, but later, through some theoretical work, it was shown that these objects describe an event horizon, which is a surface from which light cannot escape, concealing a curvature singularity at the interior of this object. The curvature singularity is a region where the space-time curvature becomes infinite, and these equations no longer become valid. So they indicate curvature singularity is the breakdown of the theory of general relativity. These objects might seem a bit weird, but there is a series of theoretical arguments that make you believe that they are actually there in space. Perhaps the most important ones are listed here. The first one is the results by Volkov saying that there are stability limits to neutron stars. Neutron stars become unstable beyond certain masses. More than that, even if you don't think about neutron stars, but just about stars in hydrostatic equilibrium, which is this balance between the gravitational pull of an object, which tends to collapse it, and the internal pressures of this object, which tends to counterbalance this effect, there is a limit to how compact any star in hydrostatic equilibrium can be, which is derived by Bugdal in his theorem, where by the compactness we understand just the ratio between the mass of the object and its total radius. Perhaps the most important theoretical reason is Penrose's theorem, which tells you that in general relativity, under generic condition, when matter is collapsing, if nothing stops this collapse, the system will evolve towards a black hole, which has a space-time, a curvature singularity. So all of these reasons together tell you that there is no alternative to black holes. Standard matter cannot be stable beyond certain masses, hydrostatic equilibrium cannot be preserved, and when you have something collapsing, you form a black hole. Together with these theoretical arguments, there are a series of observational reasons, observations of AGNs, the detection of supermassive and stellar mass candidates, also the measurement of velocity dispersion of stars around, say, J star. More recently, we have gravitational wave detection and the EHT images. So the amount of evidence is very abundant, and this is why we have this belief that the object sitting there is indeed a black hole. But as theorists, we want to question the theoretical arguments behind the possible existence of black holes to the detail. And in my thesis, I studied the Bugdal theorem, the limit to objects in hydrostatic equilibrium imposed by general relativity. We found that when you include quantum matter into the picture, the Bugdal theorem no longer holds, and you can find stars which are essentially as compact and as black as the black holes from general relativity. So they could possibly be an alternative model that could describe these very same observations. Let me talk briefly about the Bugdal theorem, because I necessarily need to do so. Consider a spherically symmetric star composed of a perfect fluid. A perfect fluid is just a matter fluid which has no shear stress, no viscosity, no heat conduction. It's just a very simple model in order to prove this theorem. It's described by the following stress-energy tensor, which is a diagonal matrix that represents the energy density of the fluid and the pressures in the different directions. The Bugdal theorem establishes that if the exterior of this star is given by the vacuum solutions from general relativity, by the Schwarzschild spacetime, if the energy density of this star is a function that decreases from the center of the star all the way towards the surface, another way of seeing this is that if you take spherical layers of the star, the larger these spherical layers are, the more mass they contain. And also if the pressures are not highly anisotropic, which means the pressures in the angular directions do not surpass the radial pressures, you can prove with this theorem that these stars satisfying these conditions will have a maximum compactness limit. A particular example is the very simple model of isotropic stars, where all the pressures in every direction are the same, and the equation of state, or the behavior of the energy density, is constant with the radius. This model describes an incompressible fluid and has been historically used to describe neutron stars. The hypotheses behind the Bugdal theorem are saturated by this model, and we find a bound to the maximum compactness of these stars, which is smaller or equal to 8/9. The compactness of a black hole is C equals 1, so we see there is a gap between the maximum compactness possible for a star in hydrostatic equilibrium and the black hole compactness. Another way to look at this result, more physical, is to think about the role of the pressure. When you have a very compact object, the more you compress it, hydrostatic equilibrium tells you that the internal pressures need to become larger and larger. There is a regime, there is a point in which, since general relativity tells you that pressures gravitate, there is a point in which they become so large that they start collapsing the object instead of preventing gravitational collapse. So you find this bound to the compactness. However, in a more realistic scenario, this star is immersed in a medium. It's immersed in quantum fields, which are physical entities that give rise to the fundamental particles. In their state of minimum energy, in their vacuum state, where there are no particles present, these quantum fields still have 0-point energies that, of course, gravitate. And they act also as a kind of perfect fluid. There is an approximation, which we call the semiclassical approximation, which includes the contribution of this vacuum fluid into the Einstein equations as an additional stress-energy tensor. In typical situations, these effects are completely negligible because they scale with the Planck constant. But there are some situations, especially when stars become very, very compact and very close to the Bookdal limit, in which this term cannot be neglected anymore, and we have to take it into account in the Einstein equations. The physical phenomenon responsible for needing to add this term is known as vacuum polarization. There is an analogy with electromagnetism, if you want, that tells us, imagine, for example, the electromagnetic field in its vacuum state. It's filled with virtual particle and antiparticle pairs, okay, which create and annihilate each other continuously. Now, if you place a positive charge in this electromagnetic field in vacuum, the particle and antiparticle pairs will perceive the presence of this charge and will become slightly polarized. So in practice, the charge becomes surrounded by a cloud of negative charge, which dresses its value slightly. There is an exactly analogous effect in general relativity, where a very compact star, through the gravity it generates, polarizes the vacuum state of all the other matter fields, which also gravitates. In essence, a very compact star will become surrounded by a cloud of negative energy. Negative energy amounts to negative mass, which corresponds to a gravitational repulsion. So this effect could potentially allow for the existence of more compact stars than the ones allowed by ordinary classical matter. All of this is a lot of blah blah, but to show some specific results from my thesis, we solved the semiclassical equations through these assumptions, and we found new stellar models that are more compact than the limit established by the Bookdal theorem. Essentially, they can become as compact as black holes. In the left side plot, in the blue plot, I'm showing the mass of the star in terms of its radius. The left side is the center of the star, and on the right-hand side we have the surface. And in the other plot, in the red plot, I'm showing the internal pressures of the star. And here, darker curves correspond to more and more compact objects. The thing that I want you to notice in this figure is that the more we compress the star, the more negative the mass becomes in the interior. And it is precisely the negativity of this mass what's exerting a gravitational repulsion capable of stabilizing the object in situations where classically it would collapse. And there is some gravitational pull. Regarding the Bookdal theorem, we calculated also the quantum density, the energy density associated to the vacuum, and we saw it's negative and very large in the interior, which makes us realize that the second assumption behind the Bookdal theorem, the one related to the monotonicity of the energy density, is no longer valid and is being violated by the introduction of quantum effects. So we broke this theorem and we found no further compactness bound to these new stars. Here, another way of understanding this is by plotting a mass radius diagram. In this plot, straight lines correspond to constant compactness values. The dark line is the black hole compactness, C equals 1. The red line is the Bookdal limit, C equals 8/9. And the blue curve is just a family of semiclassical stars that we obtained. As the star is made more compact, the vacuum polarization it generates is increasing. When we reach the Bookdal limit, classically the star would collapse, the pressures would become infinite at the interior, but we see that this vacuum polarization becomes very large and sustains the object. And finally, when we reach this phase transition, let's say, the star can be made as compact as black holes. A friend made me realize yesterday that this figure has no units. It's actually in Planck units. But also, I take the opportunity to comment that these objects do not have any particular mass scale associated. So they can describe either stellar mass black holes or supermassive black holes, because the relevant quantity here is the compactness, is how close you are to the black hole limit, not the particular mass of the object. Just to conclude, I emphasize again that we found an alternative model to black holes that doesn't have event horizons or space-time singularities, so it's well defined from a fundamental perspective. It requires no new physics beyond quantum field theory in curved spacetimes. So we just put together two ingredients, hydrostatic equilibrium and quantum fields, and found this new possibility. And we are currently working on whether these objects are compatible with current gravitational wave observations. This is a work that appeared today in the archive in collaboration with Vania Vellucci and Stefano Liberati. Finally, just takeaway message. It appears that the theoretical arguments in favor for the existence of black holes are not entirely conclusive when we include quantum effects, which motivates the need for more observations until perhaps we convince ourselves that the objects that we're seeing are truly black holes, or we find some exciting surprises along the way. Only time will tell. Thank you very much.
Samuel, are you around? Please come here. We are, lo digo en español. Vamos a entregarles una pequeña placa conmemorativa de sus premios, como es tradición.